Okay, our next speaker is Oskar Vafek from Florida State University. His title is Correlations and Topology in the Magic Angle TBG. Please go ahead.
Okay, thank you very much. I just want to make sure, can you hear me okay?
Yeah, great.
Thanks. Okay, so thank you very much to everyone, and especially to Sankar for the kind invitation. It's a real honor to be here. Sankar mentioned that we should emphasize depth over breadth in our talks as much as possible and discuss history only to the extent it is necessary to make the work comprehensible. He would rather have a very deep and small lake than a huge shallow ocean. So this is going to be my ambition to indeed dive deep into this lake of twisted bilayer graphene problem. As you will see, we think we'll discover some beautiful things on the way down, but maybe won't quite reach the bottom. So I have been very fortunate to collaborate with Jian Kang, who was a postdoc at the Mag Lab and is now on a faculty at Suzhou University in China. And large part of this talk is based on these publications and a preprint. In addition, the last part of the talk, we were fortunate to collaborate with Andrei Bernovic on the cascades transition, which was posted in this paper. Now, this was already said many, many times in this very nice conference by others. I have a benefit to not have to go through the interaction all that much, but just to set the stage for the basic physical ideas and to give you an intuition for the physics of the narrow bands, let's first consider two decoupled graphene layers. So there's no hopping between the top and the bottom layer, let's say, and they're twisted relative to each other by some small angle theta. Then let's say the top layer will have a large Brillouin zone marked by the blue with its Dirac point K1. And of course, there is the time reversal partner of it, which would be K1 prime, shown over here. The other layer has its own Brillouin zone, which is marked by the red here, which is rotated to it by, as I mentioned, this angle theta, and it has its own Dirac point K2. And so now imagine that we were to just draw the dispersion along the cut that joins these two Dirac points. It would look something like this. There would be the blue Dirac cone and the red Dirac cone intersecting each other. And there would be no level repulsion in the absence of the interlayer tunneling. And there is an energy scale associated with this level crossing, which depends on the slope. So that's the Fermi velocity. And then it depends on the displacement between the two Dirac points in the momentum space, delta K. But now if we turn on the coupling between the layers, there's another energy scale, which is set by the interlayer tunneling. I think Ashwin and Mike both mentioned that there are two parameters which describe this in the continuum model, W0, which is the interlayer tunneling through the AA region, and W1, which is the interlayer tunneling through the AB region. And that will cause this level crossing to turn into a level avoidance. Now you can kind of see from this picture that, let's say you were to hold one of these energy scales fixed. So let's say W0 and W1 are fixed by the chemistry of the bilayer, and you were to change the twist angle, then you would be changing one of these energy scales. We would be changing the level crossing energy scale, VF delta K. And then you can imagine that as you make the angle small enough such that the ratio becomes of order 1, something interesting happens, because now these levels push against each other by just about as much as there is a bandwidth. So you can hope to flatten it out at that point. The denominator here, this delta K, is controlled by the angle, and then the numerator is controlled, for example, by pressure. Let's see. So this movie on the left is supposed to illustrate this effect in a more realistic calculation, we're going to plot the dispersion of the Bissitzer-McDonald model along this particular path in the Moiré Brillouin zone, and start with a large angle that is away from the first magic angle. And of course, as we make the angle smaller, the period, the Moiré period increases, and so the Brillouin zone gets smaller. But just to illustrate this better, I'm going to continuously rescale the size of the Brillouin zone so that this x-axis will stay fixed. And then we're going to run the angle down and see, hopefully this movie is running. You can see as the bands are starting to push against each other more strongly relative to the level crossing, we find a flat band, and then the bands get not so flat again. So this is really there's really a minimum at a special value of the angle. Okay. Now I would like to make a point here. So we have heard that when we reach these narrow bands at the magic angle, there are interesting correlation physics effects that happen. And the point here, as was emphasized by Andrea and Pablo's publications, is that this is actually quite extremely sensitive to the value of the twist angle. So for example, even a 5% change in the optimal value of the twist angle can lead to more than a factor of 2 reduction in the superconducting TC, with even stronger suppression of correlated insulators. So consider now just the monolayer graphene, so not the twisted bilayer. There was a very nice paper in the 90s by Gonzalez, Paco Guinea, and Maria Vosmediano, where they studied the effect of the 1/r Coulomb interaction in a monolayer honeycomb lattice. Notice this was something like a decade before graphene was discovered. So what they pointed out, among other things, is that because the Coulomb repulsion is non-relativistic, it causes an upward renormalization of the Dirac velocity as the charge neutrality point is approached. So instead of having a perfectly conical dispersion at low energies, the dispersion will actually get steeper as the Dirac point is approached. Now, this effect has been subsequently observed by Gaiman and Novoselov. So this is the data on the dependence of the Fermi velocity as extracted from the Shubnikov-de Haas oscillations as a function of the density. So one should be thinking about the density here as giving rise to a cutoff to this log renormalization of the Fermi velocity. And they saw in the suspended samples rather large enhancement of the Fermi velocity. On the samples deposited on the hexagonal boronitride, the enhancement was smaller, but still quite sizable compared to, if we now think about it in the context of the extreme sensitivity of the correlated electron physics in the twisted bilayer narrow bands. And then there is a very nice paper from Andrea Young's experimental group and Mike's theory collaboration, where they also analyze the enhancement of VF in the hexagonal boronitride encapsulated monolayer graphene. Okay, so we see that there is at least 10 to 15% change in the Fermi velocity. Now, that would normally be of limited interest if it wasn't for this extreme sensitivity. Because as I mentioned, you see, even if you were to make a small change in the twist angle, you see this dome is very sensitive to the value of the twist angle, but the magic angle condition is actually sensitive to the is sensitive to the ratio of the interlayer coupling and then the slope times the displacement. So if you were to change this VF by 10 to 15%, you should be moving those domes around, and the magic angle condition should be changing. But this has not been observed. All right. So I will try to tell you in the first part of the talk that there's a good reason for this, for the absence of seeing the sensitivity to this Coulomb renormalization of the VF. So for the rest of this talk, we will adopt the effective continuum model of Bissitter and McDonald that was already discussed in the previous talks. And in this model, all the emergent symmetries are exact. It contains the Fermi velocity and the interlayer tunneling. So the interlayer tunneling through the AA region, as I mentioned, is marked by this W0, and through the AB region is marked by W1. Now, if you were to set this small angle rotation of this Pauli matrix to 0, it's small anyway because it's only 1 degree or so, then this model would enjoy a perfect particle Hall symmetry, as was emphasized by Andrei Brnovik's group and by Leon Balance's group. And we're going to make use of this symmetry in our renormalization group procedure that I will discuss in just a second. So there are different ways to think about this BM model, but the one that I find particularly helpful is what was introduced by Leon Balance, namely to think about this as a leading order gradient expansion of 2 coupled layers. And so the terms beyond this would be higher order in gradients. This is going to be very helpful because we can now start thinking about this through the lens of the renormalization group of some effective field theory. So now we're going to add the Coulomb interactions. Okay, so in our notation, the kinetic energy, the bare kinetic energy with all the bands of the BM model is described here. This field chi contains both the valleys, the spins, and all the bands. And the 2 valleys are related to each other by time reversal symmetry, so K and K prime. Since it's a spinless time reversal symmetry, they're related by complex conjugation. Now, our Coulomb interaction written out here has this suggestive form of delta rho, delta rho. This will actually be important in the infrared. In the UV, it really doesn't matter how you write it as long as you keep the correct chemical potential. And we can write it as this bilinear, the density minus a background term, which is there to subtract the value of the chemical potential, so that we can sit at the appropriate filling here. As I said, in the UV theory, it is optional whether you do this, but we will find this extremely useful to do so as we proceed through the renormalization. We can rewrite this anti-commutator between our 2 fields in terms of the sum over all the states below our UV cutoff, which we are going to call EC in this case. And these psi's, in principle, are exact wave functions of the Bissitter-McDonald model. Okay, so if we view this problem within the RG perspective, then we see that there are actually 3 different energy regimes. So in the first regime, the Coulomb interaction and the interlayer tunneling turn out to be perturbative. And that's sketched over here. We know that as long as the dielectric constant is at least the dielectric constant of the hexagonal boronitride, probably also in the suspended samples, there is actually no gap in the monolayer graphene. And so this tells us that we are sitting on the semimetallic side of the putative quantum phase transition. And so it tells us that the Coulomb interactions will scale effectively to 0 in the monolayer graphene, in that we will just reshape the cone. We won't open up the gap here. And so we can approach this.
Oskar, yeah. May I ask a question on this? This Please. Is not the main thrust of your paper, but as you know, I have thought a lot about this problem. Now, this is an experimental fact, and I completely agree with you that the system from an experimental perspective is in the weak coupling regime. But suppose you didn't know about experiment and you were just doing the calculation. like showing a dit for QED or something,
Right.
then it's not clear at all that Coulomb interaction is a weak coupling problem, right? Because
I agree with you for suspended. I agree with you for suspended samples. So,
I mean, alpha is 1/137, so you have to worry about a 10,000th order. But even if alpha is 0.5, you have to work. But for suspended, it's 2.2. So theoretically, we do not completely understand the issue. Do you agree with that? Because monolayer graphene doesn't open a gap.
You're saying we don't understand why monolayer graphene doesn't open up a gap if epsilon is, let's say, 10.
In the suspended, let's say in the suspended graphene.
Suspended, I agree with you. Suspended is more complicated. Yeah.
Okay. Good.
I agree with you. There's some numerical Monte Carlo on this which suggests that it may. I think it depends on the short range part, how you actually cut off the short range part. The numerics people claim, but I agree with you. I think at 2.2, it's open. Yeah, I'm actually going to. I'm going to consider the situation where we are encapsulated by hexagonal boronitride. So that gives us an additional at least 4.4.
So your alpha is more like 0.4.
Right.
Okay. Then it's not so bad. All right. Thank you.
You're welcome. All right. So so going back to our Moiré problem, as I said, we have three different regimes. We have this high energy regime, which extends from an energy scale of the order VF divided by the carbon-carbon lattice distance, maybe a little bit more than that for the distance, so that we are safe in terms of the K dot P expansion, down to an energy scale which is of order the interlayer tunneling, which we're gonna mark by W1 here. And in this regime, both the Coulomb interaction, just as we discussed with Shankar right now, and the interlayer tunneling are perturbative. Then there's another scale, another regime in which the Coulomb interaction is perturbative, that's below this, below of order W1, but still away from the narrow bands, where the Coulomb interaction is still perturbative because we have a gap here separating us from the narrow bands, but the interlayer tunneling is no longer perturbative. W0 and W1 are no longer perturbative in this regime. And then finally, we have just the narrow bands, and within these narrow bands, the Coulomb interaction is non-perturbative, and I will try to justify this. And here we will just simply switch to strong coupling. So let's start with the stage one. We do the usual thing. We split the fields into fast and slow. The fast fields will be all the fields which are in the energy window between the UV cutoff EC and some smaller cutoff EC prime. And the only thing we're going to demand at this point is that the EC prime is larger than the energy scale where the interlayer tunneling becomes non-perturbative. So we do that, and then we integrate out the fast fields, and we find to one loop a renormalization of our self-energy. This delta F is written entirely in terms of the exact wave functions of the BM model. But there's a simplification because we are in the regime where the interlayer tunnelings are also perturbative, and so we can then expand this perturbatively, this delta F perturbatively in the W's, and actually make some analytical progress in the stage one. And at the same time, this delta rho can be now written in terms of the slow fields, and there will also be a change of this background field, where now it will be the sum over all the states below the new cutoff EC prime that defines this subtraction constant. Now, as you see, what I'm doing here is just purely reducing the cutoff. I am not rescaling back the fields as is usually done in Wilsonian RG. It's a choice. You could do that, but it doesn't really make that all that much sense if you just want to zoom into the narrow bands to, in fact, continuously rescale our cutoff back to the original value. Now, technically, what that does is that it does not include in our flow equations the engineering dimension of all these couplings, but the results are exact, just as they would have been before, because what we are basically doing is we are not changing the separation between the two Dirac cones. That length scale is held fixed. In any case, so the first equation in this in here is the usual log renormalization of the Fermi velocity. So that's the logarithmic increase of the velocity. These two second equations are new. The second one says that the interlayer tunneling through the AA region does not grow under RG, does not have a logarithm. On the other hand, interestingly, there is a logarithm in the interlayer tunneling through the AB region, the W1. And if we integrate these equations, it's pretty trivial to integrate these equations. What we find is the following. The growth in the interlayer tunneling through the AB region, so W1, is precisely compensated by the growth of VF. And as a result, this magic angle condition, which contained the W's divided by H bar VF K theta, because K theta doesn't scale under this RG, that becomes an RG invariant. So that tells us why the magic angle condition is essentially insensitive to the Coulomb interactions. Now, but there is a flow in the ratio of the AB tunneling, AA tunneling to the AB tunneling, such that at low energy scale, EC star, that ratio goes down, and it goes down logarithmically. So this is what happens in stage one. So as I mentioned, the first equation tells us that the value of the magic angle is largely insensitive to the Coulomb interaction, and the second one tells us that we are flowing towards the chiral limit, which was defined in this beautiful paper by Grisha Tarnopolsky, Alex Kruchko, and Ashwin. So now in the stage two, I'm going to give you an example of how we run the stage two. We then simply numerically integrate out one band, one highest energy band, and one lowest energy band, find the change in the self-energy, rotate the resulting kinetic energy, rediagonalize, rewrite the Coulomb interaction in terms of the new numerically determined bands, and keep iterating until we reach the narrow band. And so that process looks something like this. Just for illustration, I'm showing this in the chiral limit. Okay, so you see at each stage there is a rather small change in what happens to the other bands, and eventually we are now left with the narrow bands, and this is the what we will try to analyze next. But before we do that, we need to make sure that the scale at which we stop the stage one RG is essentially independent of our choice, as long as stage one RG is under control. So nobody tells me that I should stop at, let's say, 2W1 versus 10W1. As long as stage one is still under control, I can stop earlier or later, and the result cannot depend on that. Now, we demonstrate this in this plot. So the picture on the left shows, this is not at the magic angle, just for better illustration. It shows the narrow bands together with the remote bands for different choices of the UV cutoff for the stage 2 RG. And you see the result actually still depends on the choice of the UV cutoff. On the other hand, if we rescale everything by the value of VF and W1, these results on the left, according to the equations we obtained in stage one, we find a perfect scaling collapse. So this tells us that we can stop the stage one either earlier or later, as long as it's under control, and switch to numerical RG and obtain a result that's independent of where we stop, as should happen. Now, in practice, if we were to take this cutoff to be, of order EV or even larger, then there would be thousands of bands to worry about numerically, and that's impossible. But because we have this numeric analytical insight, we can deal with the stage one analytically, and then we are left only with of order 20 to 40 bands. It depends on your choice. Already when you have 20 bands, you find this scaling collapse. And 20 bands numerically is not so bad. All right. Now, I said in stage one, we are approaching the chiral limit. How do we know that we don't reverse this flow in stage two? After all, it's purely numerical. So there are several things we can check. One of them is the sublattice polarization. I think Ashwin mentioned this in his talk. If we were in a chiral limit, then the sublattice would be perfectly polarized. So that means that these eigenvalues of the projected sublattice operators would be 1 everywhere throughout the Brillouin zone. Now we start with the bare model, which has W0 over W1 0.83. This value is inspired by the ratio of the AA to AB areas measured in STM by Ali Yazdani's group. But then we see that under RG, which has to be done numerically in the second stage, we find that the sublattice polarization is significantly enhanced. So we are indeed going towards the chiral limit. There's another thing we can check, and that's the Wilson loop eigenvalue. So let me first explain how we do this. We can consider a projected position operator with periodic boundary conditions. This position operator here, you see, is exponentiated, and this delta Q points in the direction G1 of one of the reciprocal lattice vectors. And you should think of this delta Q as something being extremely small. And then this P projects onto the narrow bands, of which there are 2 per valley per spin. And then we want to diagonalize this operator. Because there's one good quantum number, that's the momentum along G2, we can then plot the eigenvalues of this projected operator as a function of this good quantum number K. Okay, so there's some technology for how to do this. And the eigenfunctions of this, by the way, will be the so-called hybrid Vanier states. Now, these hybrid Vanier states, they are localized in one direction and extended in the other direction. Here, we resolve them per valleys, per layer and per sublattice. So this is top sublattice A, top sublattice B, bottom sublattice A, bottom sublattice B. And they're also shown at 2 different values of the conserved momentum. So this one is at 0, and this one is at 0.5 in units of G2. You see they're actually drifting, which is consistent with what Mike was mentioning, namely that we can think about the narrow bands as being composed of churn plus and churn minus. So this is what they look like. They can be made localized in one direction, but they're extended in the other direction. But you can actually see that the structure is not as simple as Lois lambda level wave functions. Now, so the eigenvalues of this projected position operator can be thought of as the expectation value of the position of the hybrid Vanier states are shown here. And different panels show different ratios of the W0 to W1. So here, this is the chiral limit. And you can see one of them drifts to the right, let's say, as you increase the good quantum number, just as, let's say, churn plus state would. And the other one drifts to the left, just as churn minus. And this is true for each one of them, okay? But so the topology doesn't change as we change the ratio, but you see that the shapes of these Wilson loops do change. And they become rather flat by the time you reach the value that is considered to be realistic. Okay, so what we can do now is we can ask what happens to the Wilson loop of the narrow bands under renormalization. And in particular, what happens to them under the second stage of renormalization, which is numerical. And what we find is that they continue steepening, just as if you took an ordinary Bissett-McDonald model and moved towards the chiral limit. So we see that there's no reversal of the flow in the second stage, and we just simply continue flowing towards the chiral limit in the second stage. So here, the blue curve is the bare value. The red curve is the Wilson loop after the stage 1 RG. And then the curves in between are the results of various numerically computed stage 2 steps. Okay. Okay, so I'd like to make a comment about the frozen band approximation, which is adopted in many papers and literature. So once the remote bands are frozen, we're not doing this here, notice, the completeness of the single particle Hilbert space guarantees that the Hilbert space of the narrow bands is frozen as well. Now, the energies of the narrow bands can change due to interactions with the frozen remote bands, but the narrow band Hilbert space does not change. And because the sublattice polarization operator and the Wilson loop eigenvalues are determined by the projection operator onto the narrow band subspace, the sublattice Wilson loops would be unaffected in this frozen band approximation. This is not what we see. In addition, the effect described here, so therefore the effect described will be described here will be missed in such an approximation, as would be the realization of W's in these Dirac C subtraction schemes that you can find in the literature. Okay, so now that we are done with the elimination of the remote bands, we are we only have the narrow bands, so this gives us a systematic way to construct a projection onto the narrow bands, and we can finally think about the problem within the renormalized narrow bands only. Okay, and so we're going to start by saying the Coulomb interaction here is non-perturbative. Adopt the strong coupling point of view, and then check how large is the residual kinetic energy by computing the super exchange exactly. Okay. So now, again, it's important that what we are left with here is this form of delta rho, where delta rho is a projected a density operator with this now renormalized background subtracted. And so, as I said, we're going to start by assuming that it dominates the residual renormalized kinetic energy. There are several statements one can make in the model in which we only keep the Coulomb interaction. So at the charge neutrality point, any many-body state that is annihilated by delta rho is a ground state, because this is positive semi-definite. In addition, ground states turn out to be many-body eigenstates of delta rho, which was shown in this very nice series of papers by Andrei Bernevik's group. In addition, at odd integer filling, if the sublattice is perfectly polarized, so we are in a chiral limit, then Chern states are ground states. But turns out these are not the only ground states, because there's an enhanced symmetry, as I will discuss in just a second. So one way or another, we should be thinking about this as generalized ferromagnets being favored by the projected Coulomb interaction. And this was sort of first pointed out in the Vanier basis in this paper, and then later discussed in the momentum basis, in the Bloch basis. So there's an important approximate symmetry, which I alluded to at the beginning, the particle Hall symmetry, which leads to another important symmetry in the strong coupling, which allows us to rotate freely between the spin and valley degrees of freedom. And it is rooted in the approximate particle Hall symmetry I mentioned, which we can define as shown here. You see, it relates the eigenstates in the narrow band nk, let's say it's the upper energy eigenstate, to another eigenstate down here via this operator, which in this particular case contains complex conjugation, and it switches the layers. So mu y acts in the layer basis, and a sigma x acts in the sublattice basis. Now, if we expand the density operator at a position r in terms of these eigenstates psi, okay, then the matrix structure will look like this. It will split into these 2x2 blocks, where the A, B, C, and D can be written explicitly in terms of size, and the symmetries relate the two different blocks. And you can just see by inspection that this 4x4 matrix for the density operator will commute with the following four matrices, obviously identity and tau z, because the two valleys are decoupled. But in addition, there are there are these other two matrices which actually change the values, and they also commute with this matrix. So the first two correspond to independent spin and valley rotations, while the second one give us rotations between the values. Now, in the chiral limit, there is a basis in which these coefficients B and C vanish, and the symmetry is even larger. It enhances to U4 cross U4, as was mentioned by the previous speakers. So what does this mean? It means that if we find one state which is annihilated by delta rho at the neutrality point, all the other states can then be obtained by performing a global U4 rotation in spin and valley on that state. And if we are in a chiral limit, then in fact, we can even perform U4 cross U4 rotation on that state. And any state within that manifold is also a ground state. So I'm going to now focus on the charge neutrality point just to illustrate some results, and then go back to other integers and try to say something in what happens in between the integers. As I mentioned, any state that can be obtained from the valley polarized state, because valley polarized state is annihilated by delta rho by the spin valley U4 rotation, is also a ground state. Now, we can actually find exact excitations on top of this ground state by noticing the following thing. In strong coupling, let's say that I act with some operator X on the ground state. And then in strong coupling, I only have the Coulomb interactions, the projected Coulomb interactions V int. Remember, these V int are delta rho times V, but each delta rho annihilates the ground state. And therefore, I can replace them by commutators. And now you see, because each of these delta rho contains one creation and one annihilation operator, they will not change the number of creation and annihilation operators in the operator X. And therefore, we can just simply match the coefficients from the left-hand side so on the right-hand side of the eigenequation and the left-hand side of the eigenequation, which would be E times X omega. And if we match these coefficients, we can then find the exact spectrum of the excitations in the strong coupling. Now let's start by setting this operator X to be either one raising or one lowering operator. So we're trying to put one particle or one hole to the charge neutrality point. This problem is relatively easily solved analytically. And what we find is the following. So first of all, these states are gapped. The gap is set by the Coulomb scale. I will come back to this later. But remarkably, despite the fact that we are in strong coupling, if we add one particle or one hole, it disperses. And the bandwidth of the dispersion is itself set by the Coulomb scale. Notice this does not happen in the strong coupling of the Hubbard model. In the Hubbard model, in strong coupling, there's no kinetic energy. If you were to add a particle or a hole, then it would just simply sit there and would cost you. But here it disperses. And the minimum of the dispersion is at the gamma point. This is actually similar to the graph that Ashwin showed from the Monte Carlo. Again, I'll come back to this as we go along. So, so now this tells you that perhaps one way to achieve itineracy in this problem in strong coupling is that once you start adding particles into the charge neutrality point, they will sit in this sort of self-generated minimum of the dispersion near gamma, and you will have small pockets near gamma. The second thing that I want to show you is an exact calculation of an excitation that's neutral, so D dagger D type excitation, on top of the strong coupling ground state at the neutrality point. So this was done after we performed the RG. So we started with the bare value of the W0 over W1, 0.83. We chose the dielectric constant to be 4.4. That's the bare value of the dielectric constant. And we have some UV cutoff, which would correspond to about 2 EV in real units. We perform the stage 1 and stage 2 RG. Then we project. So we then have the resulting problem in the narrow bands. Add a particle Hall to this and try to match the operator content on both sides and solve the Eigen equation. And this is what we get. The x-axis is the cut through the Brillouin zone. So that's the center of the mass of the particle Hall. And then you see that there are these ferromagnetic ghost-on bosons, which are quadratic here because there's no anisotropy. There are 4 of them. These are the U4 ghost-on bosons. But then in addition, there is another branch which softens. And this branch would become perfectly soft where we in the chiral limit. So if we reach U4 cross U4, this pseudo-ghost-on mode will become perfectly soft. In addition, there is an additional set of soft modes which are nematic. And then the red curve shown here is obtained from the single particle dispersion by studying the kinematics of the particle Hall. So this sets the particle Hall continuum. The particle Hall continuum starts at about 2 Coulomb units. Now, the mass or the gap of this pseudo-ghost-on is related to the anisotropy that Mike mentioned that is important for the skyrmion energetics. And in this particular calculation, we find it to be rather large. It's about 0.05 in the Coulomb units. Now, we can then ask, what happens when we bring back the residual kinetic energy? So we're going to do a second-order perturbation theory with the kinetic energy, act on the ground state with the kinetic energy operator. Now, the kinetic energy operator is charge neutral, and it is at k equal to 0. So that means that we can expand it in terms of the exact eigenstates that we have obtained numerically here at gamma. So the kinetic energy operator is going to be some linear combination of these operators here. And then when we act with it on our ground state, we have not only the matrix elements, but also the denominators, the energies of the resulting excitations. And these are the only states that the kinetic energy will couple to leading order, to second order, so usual super exchange. And when we do this calculation as a function of the angle, what we find is that there is a minimum at the magic angle for the super exchange, and that in the Coulomb units, it takes a rather small value in terms of, it takes a rather small value. So you see, it's large because the bandwidth is larger over here. Even the renormalized bandwidth is larger. Then it takes on a minimum at the magic value, and then it increases. So this is the J that is needed for the skyrmions to pair. Now you see, this J here is larger, significantly larger than the anisotropy. Okay, so if I had more time, I would have said something about additional states which are outside of this U4 cross U4 ferromagnetic manifold, which I described before. I would describe the DMRG calculation that we have done and additional variational calculations, the topology of the Dirac node braiding, et cetera, et cetera. I don't have time for any of this. Let me just say that there are additional states outside of this manifold, which are nematic or stripe states, which are also energetically competitive. And in particular, the nematic state is gapless. So in principle, we can be in strong coupling and have a gapless phase. In addition, some of these stripe states do not break C2T symmetry. Nevertheless, they gap. And the degree to which they gap depends on how strongly is the particle Hall symmetry broken. So in fact, one can be in strong coupling, not violate C2T, therefore not get any anomalous Hall effect, and still have a small gap in principle. But what I want to discuss here is 2 different scenarios for how one could think about itineracy in the strong coupling limit. So, so one option is what was mentioned by Mike in the previous talk, is that we have a strong coupling ferromagnetic phase. That phase has a texture in its order parameter, and this texture carries charge. Okay. So this would be similar to what happens in the lowest lambda level in integer quantum Hall. As Mike mentioned, skyrmions and anti-skyrmions attract, so they would give us a very nice way to think about superconductivity. Now, the question is anisotropy really that small to allow for skyrmions? In particular, the values I showed for the calculations we have done would disfavor them. Is the gap to single particle excitation small to allow skyrmions? So for example, remember that in the second lambda level, despite the fact that we have quantum Hall ferromagnetism, the skyrmions are not the lowest energy charge excitations. How do we understand the Landau fans? In particular, the well-known experimental fact that the Landau fans point away from the charge neutrality point. How do we understand the effective masses observed in quantum oscillations, which are seen to be essentially linear in the filling? So in a scenario 2, which I will try to propose, we want to think about the excitations as being the quasi-particles that come into filling these strong coupling dispersive bands. And as I will show you, they interestingly become either light or heavy, depending whether we are doping towards the charge neutrality point or away from the charge neutrality point. So in this picture, the charge would be carried by a single particle elementary excitation. And at least doping away from the charge neutrality point from integers, we think will give rise to Fermi liquids. So let me then discuss how we could understand the cascades between these heavy and light fermions in light of the experiments that were mentioned previously. We also find negative compressibility away from the charge neutrality point side. We understand the lambda level degeneracy in this picture. And interestingly, superconductivity would, in this picture, arise on the light fermion side of this doping. So let me discuss this scenario. So let me now switch to be at a general integer filling, not necessarily just at the charge neutrality point as before. We can readily generalize this eigenvalue problem to being away from the charge neutrality point. We'll pick up an additional term. And this delta rho Q now again acts on the ground state away from the charge neutrality point. But as I mentioned, those states are eigenstates of delta rho. So this piece would then just be a C number. And again, we see the same problem, same advantage, namely that the operator content of X will not change after these single and double commutators. So again, we can just simply read off the coefficients in front of the raising and lowering operators on the left and right and set up an Eigen problem. Okay. So this constant is related to the wave function overlaps. I think this was also discussed before. Okay, so let's set X to be either the annihilation operator or the creation operator. Then the first term we can think of as an exchange, and then the second term we can think of as a direct. We find an Eigen problem for this, which is a 2x2 Eigen problem. Now remember, this is a strong coupling dispersion. It depends entirely on the Coulomb interaction and the overlaps of our block functions through this fashion. Now, in the second term, you see, you will have a different sign for the commutator if you are discussing the raising operator versus lowering operator, and that will become important. So unless nu equal to 0, we will see a different dispersion for particles and for holes. Okay, so for simplicity, let us start with the chiral limit. We're going to consider an interaction which would correspond to twisted bilayer graphene sitting in between two gates separated by Xi above and below. And so we get this infinite series of image charges. And one of the parameters that we will change in this calculation would be the separation to the gates, this value Xi. Now, the excitation for the Hall, as I mentioned, will have a different equation because this last term this last term subtracts, while for particles it adds. And so let me discuss each of these terms, each of these functions separately. So the epsilon f and the epsilon h. So in the chiral limit, the two bands are degenerate, perfectly degenerate. We understand which symmetry guarantees that. And we see that there is some dependence to the range of the Coulomb interaction, even when that range actually exceeds the Moiré wavelength Lm. So the gap changes, but as you can see from this plot, the effective mass doesn't change that much. Is there a question? Okay. So that's this first term. And the second term looks very similar. Notice the scale is different. So this is still about the same width as this one. And in the second term, we see almost no dependence to the separation to the gates. Now, if you look at these curves, you see that it resembles something like a triangle lattice hopping dispersion. And in fact, this is precisely what it is. I don't have time to discuss this, but we switched to localized 2D Wannier states to describe this dispersion. And we find the hopping coefficients for both the exchange and for the direct term in terms of the Coulomb scale, which are shown here. The central term is the on-site term in the effective tie binding description of the strong coupling dispersion. And then this term over here, that's the nearest neighbor hopping. Now notice it's negative. This is why we have a minimum at gamma. And notice that its value is very similar between the exchange and the direct terms. So what does this mean? It means that if the two terms add as we are over here, then the dispersion is going to get broader. Okay, we're going to get larger bandwidth. On the other hand, if they subtract, as would happen for the whole, the dispersion becomes rather flat. So, at the charge neutrality point, the direct term is absent, and so we just simply get the minimum at gamma. However, if we're at mu equal to 1, the excitation for the hole is rather flat, and the excitation for the electron becomes broader by about a factor of 2. If we are at nu equal to 2, the excitation for the electron has even larger increases its bandwidth, but the bandwidth for the excitation for the hole changes, which means that if we were to try to dope holes here, they would go to the vicinity of K or K prime or M. You see, they would go over here. They would not go to gamma. On the other hand, the excitations, if we were to add electrons to this, they would go near gamma. And this continues up to nu equal to 3. And so in this picture, if we are at positive filling, positive integer filling, and you try to dope holes, they seem to go in as heavy fermions. On the other hand, and so that means that they're going to have high compressibility, even possibly negative compressibility, as I will show you. On the other hand, if we add electrons, they go in as light fermions with a nice dispersion. We can compute the mass of these light fermions. Oh, sorry, I should say what happens if we go away from the chiral limit. If we go away from the chiral limit, I already showed you this dispersion is very similar, but they're splittings. There no longer is a perfect degeneracy, except that the degeneracy is still preserved at gamma, at M, and at K and K prime in the Moiré Brillouin zone. But otherwise, the shape of this is very similar. So now we're going to try to imagine that when we add electrons, we're going to try to interpolate between these exact ground states at integer fillings. And we will do so using simple Slater determinants. And ask variationally what happens without breaking translational symmetry or without doing anything fancy. So what we find is that if we are at small doping away from the charge neutrality point, then the electrons go in more or less equally to the bottom of the strong coupling band near gamma. So this would give us fourfold degeneracy of the lambda levels as observed experimentally. And as we keep doping them, one of the bands will eventually separate out and fill, and that's how we would reach in this picture mu equal to 1. Now, then again, when we try to dope into mu equal to 1, we find that variationally, the best thing the system wants to do is to occupy these 3 bands equally. This would give us these 3 small pockets near gamma, threefold degeneracy of the lambda levels, until we dope too far, and at some point there's going to be a transition. Eventually, the next band separates out and occupies and becomes filled. Okay, so these hexagons here show which parts of the momentum space for which band are being occupied by how much, and this just simply continues. So this is for a situation where we allow the C2T symmetry to be broken. That's why we have gaps at mu equal to 1 here. These are current states, and at mu equal to 3. Now, in this approximation, we can compute the total energy as a function of the filling, and therefore, from the derivative with respect to the particle number, compute the chemical potential. And we see that it has this convex type shape with clear negative compressibility from the heavy fermion side as we approach the integer. We can also do this calculation by enforcing C2T symmetry. Then what we find that the mu equal to 1 state is the nematic. That's, as I mentioned, is gapless. Okay. But again, you see something very similar is happening. And when we compute the chemical potential as a function of the filling, again, very similar shape happens. So it doesn't really matter all that much for this type of physics, whether we have gapped or gapless states at the integers. You still have these heavy versus light fermions on the 2 sides. Now, this type of approach allows us to discuss the residual interactions between the quasi-particles. This is not just Hartree-Fock. You see, when you look at these double commutator and the single commutator terms, there are additional terms, and in particular in a double commutator, there are interaction terms. And so the quasi-particles interact. Now we can estimate the effect of these residual interactions on these quasi-particles. And so in particular, can we then think about this as some type of renormalized Fermi liquid, where the bandwidth is itself set by the Coulomb interaction? So if we take 2 quasi-particles which are separated by a distance r bar, which is set by the density, the deviation of the density from the integer, then the ratio of the Coulomb interaction to the kinetic energy at that filling would exceed 35 only in a rather small window of doping around an integer. And so we may think that if there's a Wigner crystal anyway, it could only be extremely close to an integer. However, if we're to actually include the additional screening due to the nearby metallic plates, with, let's say, the plates separated by 40 nanometers, then you see now at very low doping relative to the integer, the 1/r tail of the Coulomb interaction is cut off. Okay, and then we are basically just getting we would be getting back to the Fermi liquid, and that happens in a range of doping which is larger than this range. In other words, the Wigner crystal would get wiped out by the gates. And so that's one way to estimate the effect of the Coulomb interaction. Another way would be to just simply compare the typical interaction between the particles to the bandwidth, and we find that it is less than 0.3 if we are in this range of doping. So if we are, I think there's a typo here. I'm sorry. Yeah, I think this is a typo. So there's a range. There's a comfortable range of doping where the Coulomb interaction is small compared to the bandwidth. So in this region, we expect a Fermi liquid in this interval. And in this region, the bands near the gamma point are filled equally, resulting in the lambda level degeneracy 4 minus m, where m is an integer, and again pointing away from the charge neutrality point. There is a similar result for a different model by Berghold's group in Stockholm, which does exact diagonalization, and they also find clearly jumps in the occupation factors for similar reasons, sort of self-generated dispersion. So I guess I'm out of time, so let me just say one more thing. We can also compute the filling dependence of the effective mass. We find that this magnitude is consistent with what's measured in quantum oscillations. Remarkably, it seems to be essentially linear in the doping, and so this would be easily confused with Dirac revivals if you were to just look at the mass. And again, it doesn't matter whether we allow the C2T to be broken or not. And the reason why it's linear has to do with the fact that the bands are not rigid. Needless to say, this is connected to the experiments which were alluded to. These are the STM experiments observing cascades by Ali Yazdani's group, the compressibility measurements, beautiful compressibility measurements by Shahal Ilani's group in collaboration with Pablo, and also the inverse compressibility measurements by Amir Yacobi and Pablo's group's collaboration. Yeah, as I mentioned, this would explain why the Landau fans are pointing away from the charge neutrality point at each integer and not towards. Okay, so I think I'm out of time, so let me just flash my conclusions and maybe take some questions if there's still enough time. Thank you.
All right, thank you very much for the very wonderful talk. Since we are already behind the schedule, maybe at most one short question, if there's any question.
I ask one question. It's Mike Zalatil.
Sure, sure.
I think the RG procedure is super cool. It seems useful for the numerics to know that W flows so that, you know, when we project in the flat bands, we can just use a different valley. Do you have any insight into how the Coulomb interaction renormalizes? Like, will it develop a Q-dependent screening sort of thing that we could then just put in kind of phenomenologically?
It's an excellent question. So we have some estimates of this in the Cascades paper, where what we do is so strictly speaking, the 1 over R tail will not renormalize. Nevertheless, of course, it doesn't mean that we do not get a dielectric function renormalization. We compute this, we estimate this in the Cascades paper by pretending that the remote bands are plane waves, impose a hard lower cutoff, and then integrate out all of those bands and compute the polarization function. That actually can be done basically analytically. And then what you see is that the correction to the dielectric function is such that at small q, it's still 1 over q, but then at larger q, you pick up something that would look like a continuation of what you would get if you just took a monolayer graphene and integrated out everything. So in that case, you would get that at significant values of q, epsilon is about 10.
Mm-hmm. Okay.
So then in principle, you see, you could at least set up some bounds on this. In the worst case scenario, you would do the RG with a bare value of 10 and ignore any renormalization of the Coulomb interaction, and that would give you a lower bound on the effect of the interaction. Or you can just do what we did, that would give you the upper bound.
Okay, thank you.
You're welcome.
All right, let us thank Oskar again for the wonderful talk.
Thank you.